record button. Alright, so you may start. Off ko lang yung mic ko.
Good day to everyone. So we are the group 5 from and we are the reporters for today's topic. We will be discussing inelastic and inelastic response spectra. First, let me introduce to you some particular topic which can be used. First, let me introduce to you some particular topic which can be used in the application of the elastic and inelastic response spectra. Seismic analysis and design verification. With that, elastic response under moderate earthquake, collapse is precluded under severe earthquake. The important factors to be considered that influence the earthquake resistant design are the first, the geographical location of the structure, second, the site soil and foundation conditions, third, the importance of the structures, fourth, the dynamic characteristics of the structure, such as natural periods, and fifth, the properties of the structures, such as strength, stiffness, ductility, and energy dissipation capacity. These factors are considered directly or indirectly in all the methods of analysis. Building standards use hazard maps to determine a zone factor based on probabilistic hazard. Earthquake characteristics are compiled into simplified design spectra that define equivalent accelerations related to building period. At a simple level of the organization design spectrum, firmly identifies that there is a role for design in changeover improvement, even if by adopting solutions towards the organization end of the spectrum, design is frequently of a non-substantive nature. And for the general information of the elastic and elastic response spectra, what is a response spectrum? A response spectrum is simply a plot of the peak or steady state response or the displacement, velocity, or acceleration of a series of oscillators of varying natural frequency that are forced into motion by the same base vibration or shock. The resulting plot can then be used to pick off the response of any linear system given its natural frequency of oscillation. One such use is in accessing the peak response of buildings to earthquakes. A response spectra can also be used in assessing the response of linear system with multiple modes of oscillation or multi-degree of freedom systems, although they are only accurate for low levels of damping. Modal analysis is performed to identify the modes, and the response that mode can be picked from the response spectrum. The science of strong ground motion may use some values from the ground response spectrum, calculated from the recordings of the surface ground motion from seismographs for correlation with seismic damage. And if the input used in calculating a response spectrum is a steady state, periodic, then the steady state result is recorded. Damping must be present or else the response will be infinite. For transient input, such as seismic ground motion, the peak response is reported. Some level of damping is generally assumed, but a value will be obtained even with no damping. This peak response is the combined to estimate a total response. A typical combination method is the square root of the sum of the squares, or the SRSS, if the modal frequencies are not close. The result is typically different from the from that which would be calculated directly from an input, since base information is lost in the process of generating the response spectrum. And the main limitation of response spectra is that they are only universally applicable for linear systems. Response spectra can be generated for nonlinear systems, but are only applicable to systems with the same nonlinearly, although attempts have been made to develop nonlinear seismic design spectra with wider structural application, but the result of this cannot be directly combined for multi-mode response. Researchers have developed procedures to construct such design spectra from ground motion parameters. The design of the spectra should be representative of ground motions recorded at the site during past earthquakes. If none have been recorded, the design spectrum should be based on ground motions recorded at other sites under with the similar conditions. First, the magnitude of the earthquake. Given the fact the magnitude is the size of the earthquake. An earthquake has only a single magnitude, and the shaking that it causes has many values that vary from place to this is based on the distance, which comes the seconds, the distance from the site. Third, the fault mechanism. The focal mechanism of an earthquake describes the deformation in the source region that generates the seismic waves. In, in the case of a fault-related event, it refers to the orientation of the fault plane, the slip vector is also known as the faulting condition. Fourth, the travel path of seismic waves. Seismic waves travel a curving path through the earth due to changes in composition, pressure, and temperature with the layers of the earth. Seismic waves travel at different speeds through different materials. And lastly, the soil condition. Why we consider the soil condition? It is simply because a soil condition can be defined as the capacity of a soil to function with land use and ecosystem boundaries to sustain biologically productivity, maintain environmental health, and promote the plant, animal, and human health. And these are the similar conditions to be considered if none have been recorded when it comes to design spectrum.
What is response spectrum? Response spectrum is a plot of the peak or steady-state response of a series of oscillators of varying natural frequency that are forced into motion by the same base vibration or shock. Time needed to finish one complete cycle of vibration is called natural time period T. It depends on mass of the structure M, stiffness of the structure K, and when the mass increases, the time period also increases. When the stiffness increases, the time period decreases. The natural time period is T equals 2 pi multiplied by square root of M over K. Next is response to earthquake. Light frame, negligible mass, not affected by earthquake. So pagka light frame daw po ay hindi gaano maapektuhan ng earthquake. And the next is frame with mass, relative displacement, shear force, and when we multiply relative displacement Q to stiffness K equals, we obtain shear force V, which is the force to design a building, and shear force B divided by mass M equals, we obtain acceleration A. In summary, if we multiply U times K over M, or equivalent by U times 2 pi over T squared, and shear force B equals acceleration A times mass M. The next is, how do we obtain response spectrum curves? If we know the location of the building and the type of the soil, we can use one of the national codes such as ASCE 7 or the Euro code. to draw or to design response, spectrum, curve, and spectral acceleration.
Elastic response spectra. The elastic response of the actual frame to the actual loading, allowing for instability effects and assuming indefinite elastic behavior, is nonlinear, and displacements approach in infinity as the elastic critical load is approached. A close approximation to the elastic response is obtained by multiplying the linear elastic displacement at a given load factor n by the amplification factor 1 over 1 half times n over n sub c. This follows since the deflected shape of the structure is largely controlled by the sway deflections, and the displacement components of the lowest critical mode predominate as the first critical load is approached. These are the uses of elastic response. Elastic design response spectra are extremely useful to structural engineers. These spectra are the basis for computing design displacements and forces in systems expected to remain elastic. Developing design forces and displacement systems that respond elastically by modifying elastic spectrum, evaluating response of equivalent elastic structure. These elastic spectra can be obtained by several methods, which are processing of site-specific ground motion time histories, statistical relationship, empirical relationship, and code stipulations. Another is elastic spectra can be presented in several formats depending on the needs of the engineer and what information is being presented. Some of the most common formats are spectral acceleration versus period, spectral displacement versus period, spectral acceleration versus spectral displacement based on capacity design spectrum, tripartite plots such as SA, SV, and SD versus period. Also, any of the inelastic response spectrum method is a promising approach in seismic design. The present study aims at developing yield displacement spectra, constant strength spectra, constant ductility spectra, reduction factor spectra, inelastic acceleration spectra, and inelastic yield displacement spectra. Three hysteresis models. Number one, elastoplastic, relating to the state of stress between the elastic limit of a material and its breaking strength, in which the material exhibits both elastic and plastic properties. Number two, bilinear. And number three, stiffness degrading. Stiffness degradation results from crack propagation and degradation of laminate stiffness. However, previous studies on similar adherence showed that degradation of laminate stiffness is almost insignificant at the level of the loads applied here, and the degradation can therefore be attributed solely to crack propagation.
The elastic response spectrum summarizes the peak response of all possible linear single degree of freedom systems to a particular component of ground motion. It provides a practical approach to apply the knowledge of structural dynamics to the design of structures and development of lateral force requirements in building codes. So, ang elastic response spectrum daw ay parang computation lang siya ng dynamic forces, tapos i-relate lang siya dun sa static equations na ginagamit natin sa building codes. Tapos, here an example of structure subjected to force P, where properties have mass, stiffness, and damping constant. Tapos magkakaroon siya ng displacement due to lateral force P. Tapos yung the governing equation of motion of an SDF system due to applied force is Fi plus Fd plus Fs equals to P sub T, where Fi equals of mass times acceleration, Fd equals to C times the velocity, Fs equals to K times the displacement, where Fi equals to inertial force, Fd is the damping force, Fs is the restoring force, Pt is the applied force. Itong tatlong to, sila yung nagre-resist dun sa applied force. Tapos, by simplification, ang equation magiging MA plus CV plus KD equals to PT. While if the force is subjected to a ground acceleration and not in the applied force, in that case, we can convert that ground acceleration force into effective earthquake force. Kapag daw yung structures ay subjected lang siya sa ground acceleration force which is produced nga dun sa earthquake, ang magiging formula daw ay P effective equals to negative M times AG, where AG is the ground acceleration, Mn equals to mass. Therefore, yung equation kanina, magiging MA plus CV plus KD equals to negative MEG. Papalitan lang yung P force kanina, mawawala lang siya. Where C equals to negative M times damping ratio times the W, which is the natural frequency, tapos V equals to velocity, D is the displacement. Tapos, for simplification ng formula, magiging A plus 2 times damping ratio na lang siya times W times velocity plus natural frequency squared times D equals to negative AG. Bale yung mass, nawala lang siya since na-simplified nga. The deformation response spectrum is a plot of D against time t for fixed damping ratio, a similar plot for V, the velocity spectrum, and E, the acceleration spectrum. Here's the example of a displacement response spectrum subjected to a ground acceleration, deformation of a response tree SDF system with damping ratio of 2% and time interval of 0.5, 1, and 2 seconds. And ayan yung example nung response spectrum ng bawat time interval. Tapos, kinompile lang siya into one displacement response spectrum para mas maganda yung presentation niya. Ayan siya. Where set time 0.5 may equivalent siya na displacement na 2.67, time interval na 1 second, meron siyang displacement na 5.97, time interval na 2 seconds, meron siyang displacement na 7.47 displacement. Ganun din sa ibang time interval. Now, sunod naman is velocity response spectrum. Consider a quantity V for an SDF system with natural frequency W related to its peak deformation D due to earthquake ground motion. Ang formula niya ay V equals to 2 pi over T times D. Now we can use yung displacement kanina tapos yung corresponding time niya. Tapos substitute lang siya sa formula, makukuha mo na yung V so that we can graph it to a response spectrum. Ayan yung example ng velocity response spectrum related dun sa displacement and time interval kanina. So now the acceleration response spectrum. Consider a quantity A for an effect SDF system with natural frequency W related to its peak deformation due to earthquake ground motion. Ito yung acceleration response spectrum related din siya dun sa displacement response spectrum kanina. Bali kukunin lang yung displacement tapos yung corresponding time niya. And then the formula ay A equals to 2 pi over T quantity squared times D. Substitute lang yung D and T kanina. Tapos mabubuo mo na yung response spectrum na acceleration. Ayan, simple lang siya. Ipa-plot lang siya. Ganun. Sunod ay The quantity is related to the peak value of base shear or the peak value of the equivalent static force FSO. So yung mga nasolve kanina na A tapos D is i-relate siya sa sa static equation, which is FSO equals to MA. Tapos the peak base shear can be written in the form VBO equals to A over G times W, or FSO equals to A over G times W. Ayan. Ayan. Now we can proceed sa sa example na. So example, a 12 feet long vertical cantilever, 4 inches in nominal diameter, standard steel pipe, supports a 5,200 pound weight attached at the tip as shown in the figure. Tapos, the properties of the pipe are outside diameter 4.5 inches, inside diameter of 4.026 inches, and thickness of 0.237 inches. And the moment of inertia, I equals siya sa 7.23 inches raised to 4, and the elastic modulus E ay equal siya sa 29,000 KSI. Tapos, ang weight ng beam is 10.79 pound per feet. Determine the peak deformation, or D, and the bending stress in the cantilever due to the L-center ground motion. Assume that E equals to 2%. Now the solution. The lateral stiffness of this SDF system is K equals to 3 EI over L cube. So yung K na yan is para lang siya sa cantilever beam. Tapos substitute lang yung value, 3 tapos yung 29,000 kanina, tapos yung 7.23 na moment of inertia all over 12, tapos i-convert siya inches, tapos cube. Ayan, 0.0211 kips per inch. Tapos, pagkuha naman ng weight ng pipe is 10.79 yung intensity niya, times multiply lang siya dun sa whole length niya, kaya naging 129.5 pound siya. Which neglected gawa ng sobrang laki nung lump weight na 5,200. Kaya ang magiging mass na lang is W all over the gravity. Where W is yung lump weight, tapos yung 386, ayan yung gravity in terms of inches per square seconds. Kaya naging 386 siya. Equals 0.01347 kips square seconds per inch. Tapos the natural vibration frequency, or the omega, and period of the system are Wn ay equal siya sa square root ng K over M. Tapos substitute lang yung mga value na nakuha na mass and K. Makukuha mo na yung frequency na 3.958 rad per seconds. Where Wn ay equal siya sa 2 pi over T, kaya nakuha yung T na 1.59 seconds. Tapos, from the response spectrum, kung ipa-plot siya na may damping ratio na 2%, makukuha mo yung maximum displacement na 5 inches and acceleration of 0.20 G. Yan. Ayan, next step ay kapag nakuha mo na yung peak value ng displacement, makukuha mo na yung acceleration, tapos makukuha mo na din yung FSO, which is equal lang siya sa A over G times W. By direct substitution lang, 0.20 times 5.2, makukuha mo na yung FSO na 1.04 kips. Tapos the bending moment with the maximum moment at the base ay equal lang siya sa 12.48. So nakuha yung 12.48, gawa nung nag-moment siya sa pinakailalim, tapos yung 1.4 minultiply lang siya dun sa total height, which is 12, kaya nakuha yung 12.48. Tapos, by substituting ng bending stress formula, which is MC over I, makuha mo na yung bending stress. 12.48 times 12, naka-times sa 12 para maging inches, tapos 4.5 over 2, nakuha naman yan gawa nung diameter ng pipe. Dinivide lang siya sa 2 para makuha yung extreme fiber niya. Tapos divide I 7.23, makuha mo yung 46.5 KSI. Ayan, ganyan lang siya kadali, parang i-convert lang yung dynamic forces into statically forces para may apply dun sa mga NSCP book na pinag-aaralan natin.
In this lecture, we will study the concept of inelastic response spectrum, and along with that, we will also be studying the concept of several seismic design factors. The concept of inelastic response spectrum. First, the evolution of seismic design factors R, ohm, and CD in building codes. Second is the evolution of the concept of ductility in building codes. Basic design objectives of seismic resistant design. To protect the life safety of the building occupants and the general public. To control the severity of damage in small or moderate earthquakes. The expected seismic performance of buildings in different earthquake cases as follows. Resist a minor level of earthquake ground motion without damage. Resist a moderate level of earthquake ground motion without structural damage but passively experience some non-structural damage. So this is the expected desired performance from a structure in case of these two levels of earthquakes. So the response of this structure under these two minor and moderate level ground motion should be elastic or should be lightly inelastic. The main concern should be the drift control. And since the response will be elastic, so we will require the elastic design spectrum to conduct the design for these two levels of an earthquake. So we can use either the acceleration spectra for strength design and the displacement spectra for stiffness drift design of this structure under these two level of ground motion. But primarily, kailangan ng elastic design spectrum para makalculate yung effective earthquake forces and apply them statically para ma-design yung structure against these two levels of ground motion. Resists a major level of an earthquake ground motion having an intensity equal to the strongest either experienced or forecast for the building seat without collapse, but passively with some structural as well as non-structural damage. But for measure of an earthquake, ang inaasahang performance is not elastic or lightly inelastic. Ang response ng structure ay maaaring pumasok into inelastic range at maaaring magkaroon ng significant in a linear action because the desired performance. So under this kind of performance, this structure and response will obviously be inelastic response, deformation, and concern that case will be the control of inelastic deformation. In that case, we may need the inelastic response spectrum to calculate the inelastic strength demand spectra for strength design, which may be given to our structure for our desired level of ductility. Uniform building code. If we compare the base shear coefficient from the elastic design spectrum and the standard core design spectrum, for example, this uniform building code, in this case, you will observe that this line, yung mismong nasa taas na solid black line, represent the elastic design spectrum. to reduce the spectrum by a factor which can be in this range 4 to 12, and the reduced spectrum should be used sa layunin ng disenyo ng mga bagong structures. So VV in this graph is the fixed phase shear induced in a linear elastic system by strong ground motion having a VGA is equals to 0.4 G. W is the weight of the system. So based on the graph, the starting point is the PGA value. So the solid black line is representing the elastic design spectrum, and VV is the force of induced the linear inelastic system. So when we normalize VV and W, sometimes called it a V shear coefficient. And VV is same as FSO, which is elastic force, and we can normalize also W. So for different time period ranges, you can see here the elastic spectrum is significantly high compared to design spectrum proposed by different building codes. Sa Uniform Building Code, you can see here the example for different RW is equals to 4 to 12. You will be somewhere in this range and you will be designing a structure on a force which is far lower on what is required for the structure to remain elastic or the elastic spectrum. Most buildings are designed for base shear much smaller than the elastic base shear associated with the strongest shaking that can occur at the site. So the solid black line, siya yung nagre-represent sa pinakamalakas ni shaking that can occur the site. But you are not going to design your structure. Based on this line, you will reduce and you will design your structure or provide base shear or capacity of the structure based on the base shear, which is far lower than the elastic demand. Building designed by the code forces will be deformed beyond the limit of linearly elastic behavior when subjected to ground motion represented by the 0.4 G design spectrum. Thus, it should not be surprising that buildings suffer damage during intense ground shaking. So let's now proceed to earthquake response of inelastic single degree of freedom or SDF system response spectrum. This area is the force deformation relationship. During an earthquake, structures undergo oscillatory motion with reversal of deformation. So, the earthquake excitation ay magiging cyclic sa nature, so kaya ang structure ay nag-undergo in different level. Kaya ang mga paikot na deformation ay ang mga forces. Ang effective earthquake forces will be changing their directions and therefore the structures will be undergoing the oscillatory motion. The different experimental results from cyclic loading condition indicate that the cyclic deformation behavior of a structure depends on several factors, and the three primary factors are the structural material, concrete steel, the type of structural members, beam, shear member, axial member, and the last is how members are assembled into a structural system. Force deformation relation of a steel beam. For example, we have a steel beam like this, and if we apply the force cyclic in nature, push and pull, and we keep on increasing the amplitude of this force to get enough number of twine, such that we can draw this cyclic force deformation response by just applying a force and recording the U value. We can come up with this kind of a behavior where it tells us the loading and downloading unloading behavior and cyclic degradation and all other important parameters which are related to cyclic response of a particular element. This cyclic response ay tinatawag din minsan bilang hysteresis loop at maaari din itong mabuo sa ilalim ng cyclic deformation. And this hysteresis loop tells us the inelastic behavior under literal cyclic forces. So here you can see that the hysteresis loops certain drill point. It changes and it becomes soft, and when you unloaded, it doesn't come back to original position. It almost follows stiffness, which is same as initial stiffness, and has some residual deformation on the other side. Also, it follows nonlinear, and while unloading, it doesn't come back to the origin, and it has some permanent deformation. Force deformation relations of a structural steel component. As we increase the number of cycle, we can expect this cyclic degradation both in stiffness as well as in this graph. Similarly, another example, and you have a steel beam and the burning moment is of light in a cyclic manner, and for each increment the distortion. Final distortion, gravitation basically here, that particular point, and represented here at theta is recorded for each action of movement. So you can see here, this is the actual force deformation behavior, and it is an elastic or non-linear behavior. So this kind of a behavior is exhibited by steel beam, and you can see that this should be considered while calculating the inelastic response of a structure which is having this kind of behavior.
For the conclusion, elastic and elastic response spectra is a response spectrum is a graph that depicts the peak or steady state response, the displacement velocity or acceleration of a succession of oscillators with different natural frequency, all of which are activated by the same base vibration or shock. An elastic response spectrum presents a particular method for applying structural dynamics knowledge to the structure design and the creation of lateral force requirements in building codes. The inelastic response spectrum method is a potential seismic design strategy. And lastly, one of the primary goals of earthquake resistant architecture is to ensure the tenants of the building and the general public safety.